Chemical Kinetics, Part 13. Collision Theory, the three factors that affect reaction rate, and a closer look at the first of those three factors, the physical state of matter of the chemicals. The collision theory or collision model has three main parts. The first part is that reaction rate depends on the frequency of collision between the molecules. In other words, the more collisions that happen per second, the faster the reaction occurs. And the idea here is that particles have to come into contact or collide with each other if they are going to react. If the particles don't collide with each other, they won't react. But it's more than just how many reactions happen per second. Collisions must also have proper orientation of the molecules if the molecules are going to react. You could say that there are certain atoms on each molecule, or certain reactive sites on each molecule that have to come into contact during the collision. If a collision occurs but the reactive sites on the two molecules don't come into contact, then the molecules will just bounce off of each other. On the other hand, if the reactive sites do come into contact during the collision, then a reaction could occur. But there's another part to the collision model. The collisions must have sufficient energy. So if when the particles collide they don't have enough energy, they'll just bounce off of each other. Let's take a look at this analogy. Let's say I want to put this cap on this marker. And I try to do that, but they don't collide with each other with sufficient or appropriate orientation. Cap's not going to go on. If, on the other hand, I have the cap and the marker oriented appropriately, it'll go on, but if I don't push it on with enough energy, it won't stay on, it'll just fall off. So, for the cap to go on the marker, they have to be oriented appropriately, they have to collide with each other, and the energy has to be sufficient. Then the cap will go on the marker. So that's the way that works with reactions. The number of collisions that happen per second, or the frequency of the collisions, the orientation of the molecules when the particles collide, and the energy with which those particles collide, the energy with which that reaction happens, all play an important role in the rate of the reaction. Now there are three factors that affect reaction rate. In this video we're going to take a close look at the first of these three factors. That's the physical state of the chemicals. We can say that increasing the frequency of collisions would cause an increase in reaction rate. And increasing the frequency of collisions would occur for different reasons for solids and liquids and gases. So the physical state of the chemicals is important. For solids, increasing the surface area would increase the rate of reaction. Let's consider this diagram. Let's say that we have a solid crystal in this shape, and really any shape will do, but it's a little bit easier if we just take a look at this simple shape here. We could say that if a particle is going to collide with this particle and potentially react, it could collide with it on the right, on the left, on the bottom, on the top, in the front, or in the back. Now let's break that particle in two. So we no longer have one crystal, now we have two crystals. Notice that we now have two new surfaces upon which a particle could collide. That would be this shaded in surface here and this shaded in surface here. So whenever we make the particles smaller in size, that will increase the surface area no matter what the initial shape of the particles was. So increasing surface area would allow for more collisions in a given period of time, and that would mean increasing reaction rate. And that's important when we have solid chemicals. Well, what about liquids? For liquids, increasing the concentration of a liquid in a mixture of liquids or a solution would increase the reaction rate. Let's consider this diagram for liquids. Let's say that we have a liter of solution inside this container. So our total volume is 1 liter, and let's say that each dot represented here in this diagram represents 1 mole of solute that's dissolved in that 1 liter of solution. Well, that would mean that the concentration inside this container would be 10 moles per liter, or 10 molar. Now let's increase the number of particles in the container by a factor of 4. So we have 40 dots inside this shape here, inside this container. That would mean each dot is 1 mole. That's 40 moles per liter for a concentration, or 40 molar. If we introduce a chemical into this top container, the number of collisions that happen between these dots and that chemical would be smaller by a factor of 4 than they would be in this container, because we have 4 times more particles here. So increasing the concentration of a liquid in solution, in other words, increasing the amount of particles in a given space, would provide for more collisions per second, and that means increasing rate. Now let's consider gases. For gases, increasing the pressure of the gas would increase the reaction rate. Let's take a look at this diagram for gases. And you might notice that this looks very similar to the diagram that we had for liquids. You could say that for gases, it's somewhat analogous. The pressure of a gas is somewhat analogous to the concentration of a liquid. So let's say we have an empty container that's 1 liter in total volume, and we fill that container with 10 moles of gas particles. So there are 10 dots in here. We'll say each dot represents a mole of gas particles. So the number of moles in this top container, N1, is 10 moles of gas. And then let's multiply the number of moles by a factor of 4. So down here we have 40 dots. N2, the number of moles in this second container, is 40 moles of gas. Consider the combined gas law. It says P1 times V1 over N1 times T1 is equal to P2 V2 divided by N2 T2. So the pressure P, volume V, number of moles N, and temperature T relate to each other from situation 1 to situation 2 according to this equation. Now we can simplify the equation. If we have a constant volume and a constant temperature, they would cancel out from either side of the equation, and we would get P1 over N1 equals P2 over N2. We can rearrange that so that it becomes N1 over N2 equals P1 over P2. So remember, in this top container we said we have 10 moles of gas, and down here we have 40 moles of gas. So N1 is 10 moles, N2 is 40 moles. 10 divided by 40 is 1/4. If the ratio of moles is 1/4, the ratio of pressure would be 1/4. Now consider that pressure is an expression of the force of the particles hitting the side of the container divided by the area on the inside of the container. Now we said the volume of the containers is equal, so the area is going to be equal. We said the temperature is constant here, so that means that the average force with which each particle is colliding with the container would be equal. But we just have 4 times more particles down here, so we have 4 times more collisions with the inside walls of the container. Well, that would make 4 times the pressure. So the pressure in this bottom container, P2, would be 4 times bigger than the pressure in the top container, P1. Now, not only would the collisions with the side of the container be 4 times bigger, if we were to introduce a chemical into this gas to react, the number of collisions between these particles and that chemical would also be 4 times greater, just because we have 4 times the amount of particles within the same volume at the same temperature. So we can say that the ratio of the number of moles is always proportional to the ratio of the pressure. If you increase the number of moles by a factor of 4, the pressure would increase by a factor of 4. And that's why we can use pressure when we're dealing with gases, and say that increasing pressure would increase reaction rate. Now, in some later videos, we're going to take a look at the 2 other factors that affect reaction rate. We'll consider temperature, and we'll consider a catalyst. Temperature increases reaction rate for 2 different reasons. Remember that when you increase the temperature of particles, that means the particles have higher kinetic energy. So on average, the particles are moving faster. faster moving particles would increase the frequency of collisions. In other words, if the particles are moving faster, we'd get more collisions per second. But temperature, increasing the kinetic energy of the particles, would also increase the energy on average of those collisions. So not only would we get more collisions per second, but the energy of the collisions would be bigger. And both of those would promote an increase of reaction rate when we have increased temperature. Now we're going to see that higher temperature means a larger K, or larger rate constant. And that's because of these two things. Now also, in a later video, we're going to take a look at a catalyst. A catalyst is a chemical that you can introduce in a reaction, but it does not get used up in the reaction. It does take part in the reaction, and what a catalyst does is that it changes the reaction mechanism to lower the activation energy. In other words, it decreases the energy needed to start the reaction. And we're going to find out that when you have a catalyst, it will always lower the activation energy. Although catalysts can change reaction mechanisms in different ways, they all do the same thing. Catalysts always lower activation energy, and that would cause reactions to happen more quickly. In other words, it would increase the rate of reaction. And again, we're going to take a look at temperature and a catalyst in some videos coming up.